This is an image of a lensing galaxy cluster called MAX 1149. And this particular galaxy cluster is very interesting because it is a lens for a gravitationally lensed supernova. This supernova was nicknamed Supernova Refsdal, so you can actually see this cool spiral galaxy that looks kind of like it's melting. It almost looks like a little bit like a Salvador Dali painting of a galaxy. This is actually a gravitationally lensed background galaxy that you're seeing multiple images of. And you can see some of these little dots here are a supernova that has gone off in this background galaxy and then been gravitationally lensed so we can see multiple images of it. So we can actually see the same supernova going off multiple times in this image, which makes it particularly cool to see. These 4 dots are appearing in a pattern called an Einstein cross. Closer to the center of this massive galaxy, this brightest fuzzy yellow object here would be the very center of the galaxy cluster. This is where most of the mass is going to be. This is why you get the strongest distortions from gravitational lensing here. You can sort of see this third image of the galaxy that's really stretched out. You can sort of barely see it behind this brightest cluster galaxy. Gravitational lensing works where the galaxy cluster or any other massive object bends the space around it. With a massive object like this galaxy cluster in outer space, it deforms the space around it. And then as light travels through that deformed, warped space, the light bends just like looking through a glass lens. This is another view of this lensing galaxy cluster, along with a zoom in of the lensed supernova. You can see here, this is the image that we were looking at previously, along with a few extra details added. So this is our cute little Hubble Space Telescope down here, not perfectly to scale. And then you have an image of what the background galaxy would look like back here. And these white lines are kind of tracing where the light from this background galaxy would travel through the galaxy cluster. It acts as a lens. It actually bends the light rays back towards each other and back towards our telescope here. Then if we look at this zoomed in version down here, you have these 4 yellow points of light here, which are all images of the same gravitationally lensed supernova, a Refsdal. So this supernova would have originated somewhere in this galaxy, and then the light from it would travel along these different paths around this lens, eventually meeting back up at our Hubble Space Telescope. And what's really awesome about this is that by measuring the different time that it takes for the light to travel from its source to our telescope through these different paths around the gravitational lens, we can get a really strong constraint of exactly how far away this supernova is, and therefore a really strong constraint of how quickly the universe is expanding. This is an incredibly exciting image. Gravitationally lensed supernova, like the one that we're seeing in this image, is sort of a one-of-a-kind object. It really gives us a very unique look at how these supernovae can interact with a gravitational lens, which gives us a ton of additional information on both the dark matter within the gravitational lens itself and a good amount of information on how the universe is expanding. So this is kind of an open question that we're still battling with as astronomers, is exactly how quickly the universe is expanding. One of the cool things about these gravitationally lensed supernovae is that once you see one image of it, you can predict when the other images are going to show that same supernova. This Einstein cross here was the first image of the supernova that was observed, but we were able to predict that the other images of the galaxy, one of them would have shown up about 20 years prior, and then they were able to predict that actually this image over here, the lens supernova was going to appear in this image about a year after this first one was discovered. So astronomers were then able to go back with the Hubble Space Telescope and observe it about when they predicted for the second image to show up, and they were actually able to find it a year later, which was a really cool confirmation of the predictions. We were able to actually predict where it was going to be, and then it showed up, so it sort of very clearly shows that our models are working very well. This is a unique way of measuring that expansion using these gravitationally lensed supernovae. And this particular example is one of the best that we have. So this is a really incredible opportunity to study a whole lot of different components of the universe.